In Lab 8, we're going to apply the nearest neighbor algorithm to predicting which loans will be repaid and which loans will not. We're going to use data from a lending platform, Lending Club. It's a peer-to-peer lending platform. These platforms emerged in the early 2000s, where people started to use the internet to lend money to each other. This was a great innovation. There are a number of platforms these days. There's a Lending Club, Avant, Prosper, and it's beneficial to both the people who provide the loans, the investors, and people who take out the loans, because people who invest usually get a better interest rate, better return than in a traditional savings account or other investments, and people who borrow get a cheaper source of credit than, say, credit cards or payday lenders. Around these platforms, an entire ecosystem emerged whereby companies started to sell methods for doing well in these kinds of investments, helping investors select which loans to invest in and which loans not to invest in. And we're going to try to do something like that in this lab. We're going to try to find out which loans would be good and which loans won't be so good. So let's take a look at this data. We're going to spend some time exploring and cleaning the data. We'll need to normalize some of the predictor variables so that they're all on the same scale. We're going to use the KNN, evaluate the algorithms, and that will be it. So let's load in the data. It is all in loan stat3 secures.csv. What do we have? We've got 42,000 loans and 56 variables. Clearly, lots of information on each loan. We've got the ID of the loan amount. We have the interest rate, the monthly payment, the installment, where the person is employed, how long, what is their housing situation, their income, and so on. And importantly, we know the loan status. Let's take a look at the loan status. What are the different values that it can take on? It's not as simple as just this is a good loan in good standing and this is a loan in bad standing. We have loans that are charged off, meaning the borrower did not repay the entire loan. We have loans that are current. So some of these loans have not yet been paid off completely, but the borrower is current with his or her payments. So that's a good loan. Then we have some other possibilities of how Lending Club classifies a loan. The most common is a loan is fully paid. 30,000 of those 42,000 loans are fully paid. So those are all good loans. Let's try to simplify the status of the loan. Let's say that everything that is classified as current or fully paid or does not meet the credit policy but is fully paid, let's classify all those loans as good and everything else is bad. So just good versus bad. There are also some loans that have no status at all. 3 of them. Let's get rid of them right here. Let's create this new status. And we can see now we have 36,000 good loans, 6,000 bad loans. So clearly the vast majority of loans are actually repaid. Okay, let's explore some of these variables. The interest rate, if you look at the data type on the interest rate, it looks like a character, and we don't want it to be a character. Interest rate is a numerical variable. Read underscore CSV read it as a character because the original data had the percent sign in it. So we need to get rid of the percent sign and make it numeric. we can get rid of the percent sign by using the G sub function, where we specify which character we want the function to find, or which pattern, which string, because it doesn't have to be just one character. It could be a whole pattern of characters like street or road. And if you want to replace it with something else, we specify that as the second argument. In this case, we want to replace it with nothing, just empty space. And it's the interest rate that we want to replace. And of course, even after we take out the percent sign, it's still a character field. So we're going to wrap it in the as numeric function, and interest rate is now going to be, where is it? It's going to be numerical. You can see it is numerical. Let's explore the interest rates. Let's just see what this platform charges people for loans. I'm going to use a box plot. We're going to use a variety of methods in this lab to explore the data. Boxplot tells us a little bit about the distribution of a quantitative variable. And here I actually plotted it both for the good loans and the bad loans. The boxplot, clearly the box is where 50% of the values are concentrated, because the top edge of the box is the 75th percentile, the bottom edge is the 25th percentile. So 50% of all the values are between, this looks like, I don't know, 12 and maybe 17% for the good loans, and a little bit lower for the good loans. So this was the bad loans. And of course, there are some outliers. There's 20 some loans, few loans get charged 25% interest rate. Fantastic. And let's take a look at some other variables. How about we look at home ownership? Let's use a crosstab. Let's cross-tabulate the home ownership status against the status of the loan, the simplified status of the loan, good versus bad. We could see that the most common housing situation is that people rent, but there are also people who have a mortgage. Very few people actually own their house outright. In terms of differences between good or bad, it doesn't look like people with a mortgage any worse credit than people who rent. It looks like the split is roughly even, 15%, 85% bad versus good. So this doesn't look like home ownership would be a good predictor, but who knows? At this point, we're just exploring. We won't know really until we put it into an algorithm to see if that improves the algorithm's performance. But this is the first stage of selecting predictors, selecting features. Let's take a look at Fico Score. Fair Isaac Company score. This is measures credit worthiness. It's basically a reflection of one's past record of paying one's bills. So it has a history of your borrowing, and the higher the score, the better is that history. This data has FICA range high, FICA range low, because there are multiple providers, or they may have asked for the credit score at different times. Let's put it into one number that we average between the high and low. That's no problem there. And let's take a look at it. Skip the descriptive statistics here. Let's look at let's go straight up to the densities. Let's look at the density of the FICO score first. And what do we see? In red are bad loans, in green are good loans. Clearly, the good loans are associated with higher FICO scores. A lot of the bad loans have a pretty low FICO scores. Right? The distribution of FICO score is definitely to the right for good loans, and to the left for the bad loans. How about the debt to income ratio? Again, that could be a predictor. The higher the debt to income, the harder it might be for the borrower to pay off his or her loan. Let's take a look if that hypothesis is supported by the data. Again, looking at the density. So what we have on the x-axis is the variable, and we want to know how that variable is distributed. What are the most common values and less common values. These are fairly normal distributions. So most of the values are kind of in the middle, and there are a few extreme values. Overall, however, it is clear that people who default on loans have a higher debt to income ratio. And so this is consistent with our hypothesis. Fantastic. What else can we do? Oh, let's actually stop here. I think we have two pretty good candidates for predicting which loans will be good and bad. Let's start with FICO and debt to income ratio. So now, before we put that into the KNN algorithm, we have to be a little careful because we know that the KNN algorithm calculates Euclidean distances, and the Euclidean distances are scale dependent. A distance between loan A and loan B in terms of DTI is going to be pretty small because the scale of DTI is pretty small. DTI ranges from like 0 to 30. Debt to income ratio. We can see that over here. But the scale of the FICO score is much larger. So the distance between loan A and loan B in terms of a FICO score, those will be larger numbers. And so the algorithm would weigh the FICO score more heavily, would try to minimize those distances, and we don't want that. We don't have any prior as to which factor should be weighted more or less, and therefore we want to rescale them. We want to scale them so that they're all on the same scale. And how about we use a 0-1 scale? How can we do that? Well, we can take the entire column and from every value subtract the minimum number. If you subtract the minimum, then the smallest number is going to be 0. And then we're going to divide that by the range of values. So that means that when we get to the largest number, we subtract the minimum and we divide it by the range of values. The largest value is going to be 1, and everything else is going to be in between. So we can define a function. That's a useful piece of syntax to know if you want to simplify our coding instead of retyping this fairly complicated formula. Subtract the minimum, divide by maximum minus the minimum. If we don't want to keep retyping that formula, we can define that as a function, and that's what we do on this line over here. Now that function appears in our environment, and we can use it in our code. We named the function normalize because that's what it does. It normalizes a vector, a column that we specify. So let's take a look how we can apply that. Let's basically add these new columns. Let's call them FICO N for FICO normalized and DTI N for DTI normalized. And let's run that. Let's do a summary. Let's take a look at the difference between FICO and FICO normalized. Clearly, we see that the original FICO ranges from 612 to 827. The normalized FICO, as we expect, ranges from 0 to 1. Okay, and the same thing is going to be true for the normalized debt to income ratio. Fantastic. So now we have our two normalized predictors that we can feed to the KNN algorithm. But wait, before we feed it, before we train the model, let's split the data. Let's split the data into the training set and the testing set, because we want to make sure that the algorithm works on data that the algorithm didn't see. So we'll train it on one set of loans and test it on a different set of loans. There are a variety of ways we could split the entire data set into train and test. You can certainly read about the old way. Let's do it the new way. Let's set seed. We'll always do that. We'll set seed so that we all get the same values. The same random values, and let's use the function slice sample. Slice sample basically samples from a data frame. It takes as an argument a data frame, and we can specify what proportion of the original data frame we want to sample. In this case, we're going to choose 80%. We could also specify the number of samples we want to draw, but here let's do 80%. So that's going to be our training data set. You could see it has 34,000. That's 80% of 42,000. That's pretty good. How do we get the testing data? Well, the test data needs to be the loans that are not in the training data set. And we could do that using an anti-join function. Anti-join is what it sounds like. It's the opposite of a join. Instead of giving us values that match in two data set, it gives us values that don't match in two data sets. So if I try to anti-join the original big data set with the training data set using ID of the loan as the buy variables, the result is going to be data that is in the loan data set, but not in the train data set. And that's exactly what I want, because I want the loans that were not sampled when we created the training data set. So let's do that. That's 8,507 observations. Fantastic. Those two data sets add up to the original whole data set. It's a good practice to check that the train and test data sets have roughly the same proportions of the variables or the values of the variables that we're trying to predict. In this case, they do, which they should, because they were just randomly selected. It's large enough. We wouldn't expect otherwise. The split is 15% bad loans, 85% good loans. Let's run the algorithm. Okay, we're going to need the class package. We already know from lab 7 the syntax of the KNN function. It takes the training data set with just the predictor columns as arguments. The test data, again, with just the predictor columns as arguments, a vector of labels for the training data set, so that it has something to learn, so that we tell it in the training data set which loans are good, which loans are bad. We don't tell it which loans are good or bad in the test data set. That's the job of the KNN. That's what KNN has to figure out. That's what KNN has to make a prediction for. Let's choose K equals 5 so that it classifies each loan in the test data set based on the class of 5 nearest neighbors. So let's run that. Pred is just going to be a vector. We see it has 2 levels, bad or good. Well, if you look at the first 6 values, good, good, bad, good, good. All right, and goes on for basically 8,500 times, right? It classifies 8,500 loans. Obviously, KNN didn't know which loans are good, which loans are bad, but we do know that because we just hid that information from KNN, but now we can evaluate KNN's performance by cross-tabulating the actual status, which is in test $ status, and the pred vector, the predicted status. And that's what we do here on line 185. And this is the cross tabulation. So we could see in the test data set, there were 1,249 bad loans and 7,258 good loans. Of those 1,249 bad loans, we only classified 47 as bad. So those are correct classification, but certainly in terms of the share of the bad loans that we flagged as bad, that's not a particularly good record. We certainly did much better in classifying good loans as good loans. Of the 7,200, about 7,000 we correctly classified as good. Overall, our accuracy, we would add the numbers on the diagonal. The bad is 0.6%. 82.9 are the good outcomes. So overall, that's 83.5% is the accuracy. Now, clearly, we'll need to think about this, and actually, I'm going to ask you to think about this for homework. You know, is this a good performance or not so good performance? Keep in mind that if we just classified all of the loans as good, we would have 85% accuracy, because we know that 85% of the loans are good. So we clearly need more sophisticated measures of thinking about how to evaluate these algorithms. You know, perhaps we're more interested in the algorithm flagging bad loans as bad, so that we don't lose all of our money. Perhaps we care about that more than we care about incorrectly flagging good loans as bad. Sure, we're going to lose out on that investment, but at least we get to keep our money. But more on that in the homework, and certainly in lab 10, we'll definitely dive into algorithm classification, algorithm evaluation. So this gives you definitely enough to do the homework exercises. Just ask you to work with some other variables and run the algorithm, play with KNN, and I will pick up where we left off here.